Alright, another draft physics video on this circle thing, and pi, and motion, and the rules, and such. And some of it's kind of semi-irritating, but alright, so I did post the video onto the guy's video, and he said, thanks for your video. Not sure the purpose of the response video as it fails to address the whole point of my video. I don't think it failed, but anyway, which is that the experiment disproves the current formula: angular velocity equals pi times diameter times linear velocity, and unless we change pi to 4. Well, anyway, and so I commented, if you make pi 4, then you don't get the correct answer for the realized velocity, which, you know, we can talk about what kind of elements there are that have to mix to create an end result. But the point is it's an energy conservation argument, and so even if you can say that pieces, well, it's like the Miles Mathis makes the exact argument in the sense that he makes the error of starting to talk about a benefit from gravity in the running track scenario because of the lean. And that benefit is one you don't realize, because what you gain leaning, you lose straightening up. So there can't be any realized gain. So again, it's an energy conservation thing. It's like the Super Ball thing, right? A Super Ball appears, okay, to have more energy. But what it really is doing is just efficiently bouncing. It's gaining a much higher percentage of reflection. So it's a more perfect reflection. That is, it's creating less, what you would call impact damage. It's leaving less of the energy behind when it reflects off of something. So it appears that it's more energetic, that somehow there's an energy source, but there's no energy source. It's just a more perfect reflection. So it's still just the energy going in that's coming back at you. Alright, and that for x4, I mean, you know, times 4 gives you the circumference of the square you could enclose the circle in. So then he says, excellent summary of the experiment. He says that to everybody. Anyway, to understand why we need to take the enclosed square, you can find more in the reference paper. But mainly it is that for continuous curved motion, you need to take both x and y paths in the same time interval. Well, again, continuous is a key point here. So that's the fundamental argument. When you change the path length, the circle length, then you're going to be adding or subtracting energy from the thing. So if you think of this as the spinning thing on a string, if I start pulling the string, so if I'm spinning something and I can pull the string through my fist to make it a tighter circle, then I'm adding force, obviously, in a kind of obvious way. I'm pulling, so I'm injecting a force, and so now the forces can add. So now the velocity can stay the same in the forward direction, and it's an additive velocity inward, and so it will move faster. And that's the same thing as what gravity does, as I tried to point out. The difference between this experiment, or a running track, and gravity, which Newton was describing with the equation, is gravity is free. It's a force is applied, added to the other vector. So you don't need to find a source for the added vector. When there's no adding, when there's no force injecting, then you have the rebound problem. You have the Super Ball problem. That you can maximize the reflection by eliminating friction, but that's all you can do. It still has to reflect. So the point is that when something goes around a curve, what it's really doing is reflecting around the curve. Okay, so if this is the curve, it's not a very good drawing. Maybe I'll use another color for any add-ons to it. You could essentially look at it, and again the box would be so, and somebody else brought up ellipses and other things, and some other guy brought up time dilation, which I think is a real stretch to apply time dilation into an equation of such subtle difference in velocity. I just don't think you can get away with that rationally. And so this is what I was talking about, is that this is just the diameter. So this length of this box is the same as the 4 thing. Obviously, diameter 4 times is a box. And so that's what is being changed in this thing's momentum is that it's being forced to do these corners. And those corners are essentially what's taking its speed. No, it's changing its velocity. Not its fundamental velocity, its realized velocity. Because it will return to its original velocity once it gets out of the curve. Okay. So the point I'm making is that this is basically a phenomenon of just reflection. So this is a hard surface essentially, and what's happening is the thing has to hit the surface, it has to bounce off, it hits the surface, it bounces off, it hits the surface, it bounces off, and that this aleasing is essentially this amount of distance. So in sense it is traveling the square in distance. So its internal velocity, okay, is still the same. It's still moving all the bits when you add them all up. It's still moving the same speed, but it's traveling more distance essentially, because doing this reflection is basically converting this motion, this direction, and it's converting it into this direction at this point in the curve. Obviously these arrows change for each turn. And as I pointed out, to do that, it has to take some of this as a reflection. So it has to kill some motion in this direction to create this direction out of it. Where in a gravity scenario, like I said, you would have a length of velocity, and the gravity is adding another vector of velocity. So you don't have to kill velocity to add velocity. You can combine them into the new direction that will have both as the consequence when it is released. So if you could release things from gravity by just killing the gravity, it didn't have to exit the gravity, that would be its realized speed, is the speed of the acceleration of the gravity plus the real velocity of the thing. You know, and you can use these examples. So Miles Mathis is implying that you can, what do you call that when you gain speed from gravity? A gravity assist. So that's possible to have a gravity assist in, say, a running track circumstance. And it's not even possible to have a gravity assist, really, in any circumstance where the track has a fixed center of gravity. So if you fix the center of gravity of the thing you're orbiting, it really doesn't matter whether you ellipse, whether you go around it in a circle. It doesn't matter what you do. You can't gain anything if this center of gravity doesn't move. So if this isn't moving, you can't have a gravitational assist from the outside of the gravity. From interiors of the gravity you can create an assist, but it's going to be obviously artificial because you've already done part of the work of getting into the gravity you're gaining an assist from. You've already gained your gravitational acceleration. Yeah, so the real gravity assist is really just, you have to be able to steal it from the center of gravity of the thing you're going to be assisted by. So in the sense, if you're going to gain extra movement by going in a gravitational assist and going through a gravity and coming out faster here, then if you're going faster in this direction, you have to force this thing to move that way. It has to have the equal and opposite reaction. So the same mass equation spread over its mass. So maybe you're 1/millionth of the mass of the thing that has the gravity. So obviously this will move 1/millionth the amount that you move per second. But the fact is, it will do the opposite reaction thing. So you either have to make a standing object gain acceleration in the opposite direction, or you have to take the movement of an already moving object and steal its forward movement, some percentage of it, by creating a kind of friction. And that's the key word here. I mean, I use the word friction, but I guess there should be some other term used for the kind of friction that doesn't create waste. So friction that doesn't have heat or some permanent displacement of matter. So if you don't permanently change matter in a process of interaction, then what the friction is really doing is providing you a medium for reflection. It's being depressed like a piece of rubber or a piece of foam. You could push it in and it pushes back out again. That's essentially what's happening in this circumstance of this hoop. Is if you've reduced the friction, then what you're really just doing is doing a compression of the magnetic connection between the protons and the electrons. You compress them and they rebound. So you're getting the benefit of the rebound. And if it's like I said, if you do it to a high efficiency, you won't lose any of your absolute velocity. So when you leave, you'll have the same velocity as when you went into the hoop. But while you're in the hoop, you're constantly converting one direction into another direction. You're not adding vectors, you have to be subtracting, because there's only one vector that has force, and that's the thing moving. Without any of the other parts moving, there's no other source of force or movement. So any change has to be through reflection of your own momentum. You have to reflect part of your own momentum to move you in the other direction. So I could illustrate that or explain that. And this might not be work, but I just thought I would use it as an explanation of how, like I said, the interior reactions inside of matter don't work this way, but I'm just going to use this as an example for the idea of what the mechanism of a wasteless friction or adhesion would do. And this wasteless adhesion would be that, say something straight came into this, and this was a springboard. Okay, when this straight thing comes in, it compresses the springboard, and then as it's flat with the springboard, once it's compressed it, so now the springboard is compressed, and the thing is sitting on top of it. The springboard bounces back, so it pushes this tail out. So now this thing could acquire spin. Alright, but that spin is again just a piece of, that's just a transfer of the energy, and now the energy is moving in that component. It's maintained this component, but this, when this swings out, it will make this move slower. So the head can't move at the same speed because the tail is going to drag it the opposite direction. So the injection of spin will force an opposite reaction, and the opposite reaction will have to come from the forward momentum. So that's a way of understanding it, is that once I push its tail to spin it, I'm going to create an opposite reaction on its forward motion of the vector going down. So you just kind of have to realize that the force vectors have to be complementary. You can't if the thing's moving this way, as soon as you have anything that's off of this right angle, a force coming this way, it's going to be totally destructive. It's just going to kill. It's not going to be able to do an exchange. So it's only force coming from these angles that can create a change of this momentum, but it has to be out of this momentum. I think I sort of got that explained, but you can sort of understand that this spring popping up and down is a conservative event. The loss to compression is the same as the gain from its expansion. So as the front end compresses it, you also have to understand that the front end is going to it's going to acquire some movement in this vector. And then once it's compressed, it's going to require even more of it on its tail. So it's this, and like I said, it might start spinning. But the idea of you increasing its spin would be just another way of capturing the momentum. The forward motion is destroyed. The spin creates the motion to the left. And through that process, by the time you finish, you would end up with something not spinning and leaving with the same velocity it went in with. Alright, so what else did I... So again, I just wanted to stress that you can't gain from gravity. So people running on a dirt track and leaning, they can't have a gravity assist because they have to give that back when they straighten up on the straightaway. So that's just a conservation rule. So there's no gravity assist. Now there's lots of mechanics to, like he even started describing how when the runners are running, they can use different muscles because of their lean, or because they're going through a curve, they're going to use one leg more than the other, and this way they can add energy. But they really can't, because we know that the real race is about endurance, and that the overall expenditure of energy is what we're talking about over the whole race. And so it really doesn't mean anything to say I have some reserves that I can expend. If you give me a track of a particular shape, I'll be able to expend them in some new way. So we're just talking about the fact that there is going to be extra friction. I mean, you're going to lose more momentum. Every runner going around the curve, no matter what curve he goes around, is going to lose momentum to wasteful friction that he doesn't have on the straightaways. But that has nothing to do with pi equaling 4 or some kind of mathematical equation that describes the percentage of loss, this stuff. So the stuff where the square turns into a circle, that's always proportional, just like pi. So every circle you draw, no matter what size it is, the square can be drawn around it, and the stuff in this white space is always the same percentage, just like pi, 3.14. That percentage of white space is exactly the same also. And so no matter how big a loop you make, the percentage that you're really making up for, the amount of leasing you're doing, is always going to add up to you running the square. So in fact, your momentum will run the square in terms of time. Okay, so in a sense your velocity is increased, but it won't be visible velocity. It'll only be velocity because you're converting the momentum from momentum going in one direction to a momentum going in a new direction. And in that process of conversion takes time and creates more distance, in a sense. How to say it? Well, I think you can sort of understand what I'm saying. That the fact that the actual distance traveled is the square, because you're going to break it up into a bunch of reflections to do the circle. The circle is going to force you to do reflections. The amount of the reflections will equal the larger distance of the square, and that's why the actual momentum equals 4. So the amount of momentum it has is the straight line, but the circle automatically requires you to do reflections, and the reflections will change your realized velocity. As I use the term realized velocity, it will be slower. And it's only in the circumstance of gravity, or like in a nuclear accelerator where they use magnets. If you apply a force, forcing something into a circular path, then the velocities can add. But you have to apply a force for the velocities to add. Otherwise, the only momentum you have is the object you're forcing to change. And if you force a change without a force doing the changing, then the only place you can get the energy from is the thing that's moving. It has to sacrifice some of its energy to create the energy of the change in direction. So essentially it's a reflection. Alright, that's probably enough. And depending on the efficiency of the reflection will tell you whether it's going to equal this 4 thing. If it's perfect, you'll get 4. But it's still not pi. It's still not a meaningful representation of the truth, because there's no way something can travel the circle unless you create energy, unless you give it more energy. So unless you create more energy from the outside to do the bending will consume time, and it will slow the thing down. So the thing can't maintain its speed going into a circle unless you do the change of direction with more energy, like hitting it with cue balls or something. So if you hit a ball that's moving with cue balls to force it to bend, it won't lose velocity, it'll gain velocity. Okay, so I think that's enough. Yeah, I did my job again. Alright. I hope that clears it up. There was a comment on my video, but I don't think it's terribly relevant, but I might as well read it just to be safe. Oh dear, it's very long. So maybe it's not worth reading. You should try to take some time to read Miles' paper on pi. Yeah, well, I'm just saying, obviously he's made 2 fundamental mistakes, at least that I found so far. One, you know, this whole idea that you can have free, that you can do a gravitational assist. You can't do that unless you move the track. And I can't remember what the other one is, but they're fundamental mistakes. The issue is much deeper than you realize. No, I think you're not realizing that the deepest issue in physics is conservation of energy. And until you figure out where the energy is coming from to change something's direction, you don't have an argument. As for your argument about speed changing due to addition of centripetal force, it seems to be invalid. See, so I don't need to see this, because again, it's the centripetal force of uniform circular motion. So again, we're in a uniform circumstance. And in that circumstance, once something's inside the circle, it has to be using its own velocity to create the change in direction. It has to be made out of reflected energy, because there's no source of energy. The idea that an unbalanced force can change the direction and velocity vector is not magnitude, but not its magnitude, may seem a bit strange. No, that's exactly what I'm saying. So again, yeah, I'm just saying, I think you're not understanding my point, and I don't think that's my fault. Let's see, so is this guy who got into the relativity stuff? Force can indeed accelerate an object by changing its direction. Well, again, force from where? So again, without an extra, like I said, in gravity, all right, it doesn't slow down. Without something that's adding force, the only thing that has the momentum has to have it changed. Okay, Miles Mathis is conflating. No, we don't really need to bother with that. Well, anyway, somewhere in here was some mention of relativity, and I'm just saying there's no point in adding relativity to this. Some other guy made a video. Yeah, he actually did that in a video and pointed out that you have to change the reference, so you can only view it from, you know, interior to the circle. And that's that relativity nonsense of the frame crap and moving the frame, in my opinion, is silly. The physics is absolute. There's an absolute frame, and in the absolute frame, obviously the velocity is decreased. Obviously. Okay. It's consumed by the process of reflection. And I'll leave it at that. So, till next time, and such.